Hello everybody, we are going to discuss now the multiple steady states and stability analysis of CSTR. We shall follow the textbook by Fogler and with some inputs from chemical reactor analysis and design by Rawlings and Eckert. And we will also use the simulation software Reactor Lab, and I am grateful to Professor Richard Hards of University of California, San Diego for permitting me to use this software. This is available freely on the net. The module outline: number 1, multiple steady states of CSTR, and number 2, dynamic analysis of CSTR stability. First, we will start with multiple steady states in a CSTR. This is a CSTR with cooling jacket. We will discuss all these issues with a very simple case: first order irreversible reaction, liquid phase reactions, and this is CSTR with the usual nomenclatures. The exothermic reaction is taking place. There is a cooling jacket. First, we write the mole balance equation, and X mole balance is given by k tau by 1 plus k tau, that is equation 1. Then we write the energy balance equation. If the first one is the heat added term, is the heat absorbed by the feed to get heated up to the reaction temperature in the reactor, and this third term represents the heat generated due to the chemical reaction, and conversion obtained from the enthalpy balance is given by equation 2. This two curves, one representing the fractional conversion obtained from mole balance, another the fractional conversion obtained from the energy balance. It is plotted against T. The energy balance line is reasonably linear, while the mole balance line is highly non-linear in nature. The two curves, one curve and a line, will intersect at a point which is the operating point, and we get the reactor temperature and the exit conversion. Now, we can see that because the mole balance line is highly non-linear, due to some changes in the parameters, the mole balance curve and the mole balance from the energy balance curve, they might change their positions, and it is possible that more than one points of intersection occur. Now, we study this through heat generation and heat removal curves. So, first we start with the same equations, energy balance equations and the mole balance equations, and we replace the conversion term here, fractional conversion term here, by the fractional conversion obtained from the mole balance, that is k tau by 1 plus k tau, and if you multiply this k tau by 1 plus k tau with this heat of reaction term, we get the G of T, that is the heat generation, which is given by equation 3, and the numerator in the equation 2, that basically represents the heat removal, that is R of T, which is written conveniently as Cp naught into 1 plus alpha into T minus Tc, where Cp0, alpha and Tc are defined in equations 5, 6 and 7. At the operating point, the heat generation is equal to the heat removal. So, we write the heat generation and heat removal is equal to the heat generation, and when we solve this equation 8, we get the operating point or the steady state. Now, the heat generation curve, this G of T, if it is plotted against T, it is sigmoidal in nature, and its sharpness increases as the activation energy increases. and also its sharpness increases if the space time increases. For the heat removal curve, if we increase the feed temperature, the heat removal line will shift parallelly to the right, and if we increase the value of alpha, that is the value of u or a, they are increased, or the value of f a naught decreases, then with an increase in alpha, the slope of this heat removal curve will increase. Now, we plot the heat removal curve and the heat generation curve in one single diagram. So, it is plotted against T, and this blue line represents the heat generation curve and the red straight lines represent the heat removal curve. We start with a very low feed temperature of T01, corresponding to which the Tc value is Tc1, and we find that the steady state is at 1, point of intersection is 1. So, the steady state 1, the reactor temperature is Ts1, you drop a vertical, we get that. If we increase the feed temperature to T02, we find that the heat removal curve has touched the heat generation curve at the point 3, and we have got 2 points of intersection. So, 2 steady states, 2 and 3. If we increase the feed temperature even further to T03, we see that there are 3 points of intersection, 4, 5 and 6. If you increase the feed temperature even further to T04, the heat removal curve touches at the heat generation curve at the point 7, and there are 2 steady states, 7 and 8. If we increase the feed temperature even further, we see that there is only one steady state, that is 9. So, we see that if the feed temperature is below T02, only one steady state is possible, and that is at the lower level, and if the feed temperature is beyond T04, then again only one steady state is possible, and that is at the upper level. And we can also see that if you start with T01 and go on increasing the feed temperature, we will attain the steady state 1, then 2, then 4, then 7, corresponding to feed temperature T04. If you increase the feed temperature just a little bit, then it jumps to the upper steady state, which this phenomenon is called ignition, and this corresponding feed temperature of T04, where the ignition is taking place, is called the ignition temperature. If say we are operating at the upper steady state level, say at point 9, go on decreasing the feed temperature, go from 9 to 8 to 6 to 3, when its tangent heat removal curve is tangent to the heat generation curve at point 3, corresponding to the feed temperature of T02, and if you decrease the feed temperature little more, then it drops to the lower steady state level. So, this phenomenon is called extinction, and the corresponding feed temperature of T02 is called the extinction temperature. Now, we have seen that there are 3 levels of steady states. One is the upper steady states, that is 3, 6, 8, 9. One is lower steady state level 1, 2, 4, 7, and another is an intermediate steady state. 5.5 is one such steady state. If we operate at upper steady state level or at lower steady state level, say we are operating at point 9 up and upper steady state. If you slightly increase the reactor temperature, we find that heat removal is more than the heat generation. As a result, the reactor temperature will try to drop and retain the original steady state at 9. Similarly, if you decrease the reactor temperature a little bit, the heat removal is less than the heat generation. As a result, the reactor will slightly get heated up to regain the original steady state at 9. So, we see that the steady state at upper level is locally stable. We will observe the same phenomenon at the lower steady state level also, but what happens in the with the intermediate steady state, say at 5. Suppose we are operating at the intermediate steady state at 0.5 and we increase the reactor temperature a little bit. Here we will see that heat generation is higher than the heat removal and the reactor will tend to get heated up more, and as a result the reactor will move towards an upper steady state level of 6. Similarly, if the reactor temperature is slightly decreased, we will find that the heat removal is more than the heat generation. As a result, the reactor will tend to get cool down and it will approach towards the lower steady state level of 4. So, we see that this intermediate steady state is highly unstable. And as an analogy, we can see that the upper steady state level and the lower steady state level is like this marble. If you give it a perturbation, it will again regain his original equilibrium position. But if the marble has got this configuration, this is at a steady state, but if you give it a little perturbation on either side, it will roll down to achieve a new equilibrium and it will not regain its original equilibrium. Now, this lower steady state or upper steady state, in which regime the reactor will operate, sometimes we need to know that. And in a few reacting systems, this upper steady state level is not advised, because the reactor temperature will be high, and at that high reactor temperature sometimes undesired side reactions may take place, and also some vaporization of the reaction materials might occur. So, some people do not in some reactors this upper steady state level should not be used. So, this condition we call it runaway condition, or that is the in ignition level or at upper steady state level. Now, we see that when the heat removal line is at a tangent to the heat generation curve at 0.7, this point is very critical. If you slightly decrease the slope of the heat removal curve, we can see that the steady state jumps to the upper steady state level. So, that means when this 0.7 is very critical, beyond that 0.7, if the slope of the heat removal curve is less than the slope of the heat generation curve, then it reaches the upper steady state level or a runaway reaction will take place. So, what is the criteria for the runaway reaction to take place? We see that at 0.7 the heat generation is equal to heat removal. So, equation 9, the corresponding reactor temperature is T star. So, this R at T star is given by this, and G at T star is given by this, equation 10. And also we find that at the point of tangency, the slope of the heat generation curve is equal to the slope of the heat removal line. So, that is given by equation 11. This is another condition. So, we get the slope of the heat removal line at the T star is this, and we find out, we differentiate G of T with respect to T at this 0.7, that is at T star, we call it A star, and this we find that this is the slope is G of T star into E by R T star square, or in other words it is this is the G of T star into E by R T star square. So, these two will be equal, this one and this one will be equal. So, that is given by equation 12. Now, we divide equation 10 by equation 12 and we get this these two terms will get cancelled. So, with T star minus T c is given by this R T star square by E by equation 13. So, this difference T star minus T c, this is the maximum difference between the reactor temperature and T c, which can be permitted to operate the reactor, so that it does not move into the runaway reaction regime. Now, this equation 13 is basically a quadratic equation which we solve and which gives us the value of T star, expression for T star. Now, at this T star we find out the value of G of T star, that is the heat generation, and we find out the slope of the heat generation curve, that is the first derivative of G of T star, and we get this. And now, this is we find that it is a function of T star, and the T star is again a function of T c. So, at different values of T c, we calculate the values of S star and we plot it, S star versus T c. Now, the slope of the heat removal line is Cp 0 into 1 plus alpha. So, we draw a straight line here. Let us use a very small operating this feed temperature, say T 01. So, corresponding to that T c value will be T c 1. Now, here you see that this is the slope of the heat removal curve, and this is the corresponding slope of the, that is S star, that is the slope of the heat generation curve. So, you see that the slope of the heat removal curve is greater than the slope of the heat generation curve. So, it is stable in a sense that it is not entering into the runaway condition. Now, if we go on increasing the feed temperature, you see we move along this line, and the moment we cross this curve, we find that the slope of the heat removal line is less than the slope of the heat generation curve, and we have already seen that runaway conditions occurs when the heat removal curve slope is greater, the heat generation curve slope is greater than the heat removal curve slope. So, whatever we have discussed so far, that is the multiple steady states and their stability, these were all based on steady state analysis, that is we neglected the unsteady state terms or the accumulation terms in the mass balance equations and the energy balance equations. But to have a comprehensive idea, knowledge about the reactor stability, we need to carry out the dynamic analysis, and particularly that is important if you want to study the startup of a reactor. So, now we just give a very brief overview of the dynamic analysis of CSTR stability. Now, we write the transient mole balance equation and an energy balance equation, that is, this is the unsteady state term and these are the other terms for mole balance equation, and there is a enthalpy balance equation, this is a unsteady state term. So, we see that the unsteady state terms of both the mass balance equation and the enthalpy balance equation, they are a function of concentration Ca and T. So, we define this function as f1 and f2. Now, the value of this function will be 0 at the steady state, because the accumulation term will be 0. So, we see we get equation 20 and 21, that is f1 at the steady state and f2 at the steady state, they are 0. Now, we expand those functions f1 and f2, which are a function of Ca and T, in terms of Taylor series expansion around the steady state, and these steady state terms are 0. Now, we define this denote this Ca minus Cas as epsilon 1 and T minus Ts as epsilon 2. So, we rewrite the mass balance equation by equation 26 in terms of epsilon 1 and the energy balance equation in terms of epsilon 2, and we generalize it as d epsilon by dt is equal to Jacobian J into epsilon, where epsilon will have two elements, that is epsilon 1 and epsilon 2, and J will be the Jacobian of f 1 and f 2 with respect to C 1 and C 2. So, when we differentiate f 1 and f 2 with respect to C A and T, we get these elements. So, these are the elements of the Jacobian matrix. Now, we know that for the stability criteria, the eigenvalue of the Jacobian must have negative real parts, it is mandatory. If this stability criterion is not satisfied, the reactor will become unstable and it might lead to sustained oscillation. So, this is a case where that criterion was not satisfied and it has undergone sustained oscillation. So, conversion versus time, we see that it is oscillating with time, not damping out in the long run. Similarly, the reactor temperature is also oscillating with time, and at any point of time we will get the conversion and temperature values, and if we plot the conversion versus temperature, which is called a phase portrait, and if we follow the timeline, we will find that we will fall into a loop which is called a limit cycle corresponding to this sustained oscillation, and if you encounter this, it is very difficult to control the reactor. Now, we have seen that reactor instability will depend on a particular criterion, and what was a criterion? The criterion was that the eigenvalue of J must have negative real parts. Now, the eigenvalues of J will depend on the elements of the Jacobian, and the elements of the Jacobian will be determined from the parameters that we have used in the mass balance equation and the energy balance equations. So, we see that the stability criterion will depend on the different operating parameters that we have used in the mass balance equation and the enthalpy balance equation. So, here today we will study the effect of some of these parameters, just 3 of these parameters, and we will see that whether this will really show the sustained oscillation under when the criterion is not satisfied. And we will find that we will have a look at it through the simulation software. We will find that sustained oscillation and limit cycle reactor instability will be encountered at high activation energy, high value of heat of reaction and low rate of heat removal. For this simulation study, a very simple reaction has taken place, and these are the base data which have been selected. We run the Reactor Lab software, and these are the base data, and these base data, if you calculate the stability criterion, we will find that it is not satisfy the stability criterion, and then it should show the sustained oscillation. Let us see whether it really shows a sustained oscillation. So, here we see that it is showing the exit concentration, and this is the reactor temperature with respect to time. So, here we see that a sustained oscillation is experienced. Now, we will study the effect of activation energy. The previous activation energy value was 200. So, let us make it 150 and see what happens. So, we are reducing the activation energy, and let us see what happens. See, this is the exit concentration and this is the reactor temperature. Now, we see that the reactor is attaining a steady state. So, the reactor has become stable. Again we go back to activation energy of 200, we should expect the oscillation to come back, and let us see what happens. So, we find that again the oscillation has come back. So, we have seen the effect of activation energy. Next, we will assess the effect of heat of reaction. Presently, the heat of reaction is minus 250 kilojoule per mole. Let us make it minus 100 and see what happens. That is, we are reducing the value of heat of reaction. Earlier it was oscillating now we see that again the reactor has become stable. Again we move it back to minus 250. Heat of reaction, again the oscillation should come back. So, again the oscillation has reappeared. So, we see that if the heat of reaction increases, there are more chances of reactor instability. Now, we see the effect of heat removal. Presently, it is 20 kilojoule per second per Kelvin. We increase the heat removal rate. So, to 40. So, from 20 we have increased the heat removal rate to 40, and we see that the oscillation is gradually damping out, and it will take some time to get stabilized, but then it is tending to become stable. So, when we have seen that as the heat removal rate decreases, there are more chances of reactor instability. So, we have seen that as heat the activation energy was if it increases, the reactor may lead to sustained oscillation. If the heat of reaction increases for this exothermic reactions, it may lead to sustained oscillation. If heat removal rate decreases, it may lead to sustained oscillation. So, to summarize, we have discussed different multiple steady states which are possible in a CSTR, upper steady state level, lower steady state level, unstable intermediate steady state levels we have discussed. We have also discussed ignition and extinction temperatures, the runaway reactions, the criterion for that we have developed, and also we have carried out dynamic analysis for CSTR stability, and we have discussed about the stability criterion, and we have carried out simulation studies to investigate the effect of activation energy, heat of reaction and heat removal rate on reactor instability, and we have seen that high activation energy, high heat of reaction and low heat removal rate encourages sustained oscillation and limit cycle, that is lead to reactor instability. Thank you.